Hello, Lee. Hello, Lena. Glad you're there. That's good. So Nicholas, Natalie, and Isabella, hello. Dynamite. Priya, hello. Glad you can all be there, 10E. Hello, Julian. And hello, Marilyn and Magdalena. Hello, Lily and Dominic. Great. Hello, Julian L. And I did get a haircut. It's shorter. But I didn't do it anywhere else. I had it done at home. How about that, huh? Okay. Julian L. Gotcha. All right. Vincent, Larissa, and thank you. Vincent, Larissa, and Shilpa. Hello. Vincent, Larissa, and Shilpa. Hello. Great. Okay. It's certainly nice to have shorter hair. For a while, I was feeling like one of the Beatles from the 1960s with this big mop of hair, you know? Crazy. I couldn't hardly see anything. Okay, who else I got? Let's see. Are you out there, Noah or Sarah, Aiden, Tadashi, Deacon Riley, Tom Christian, or Ali? If you are, say hello. How are all of you doing? I hope, are you staying sane out there in homeland? From what I hear, we may have the 11th and 12th graders going back starting the 9th of March. But for 7 through 10, I think you'll still be online for a while. There's a couple more. Do we have to send in a picture of the alcohol worksheet? No. No, just fill it in, but that's not much of an assignment. It'll take you just a minute. Fill in the little parts of it, but that's all you need to do. Don't send me a picture. I got enough emails of that for real assignments. Okay, hello, Sarah and Riley. Hello, Noah and Tadashi. Hey, now we're rounding everybody out. That's really good. Still looking for Aiden, Deacon, Tom, Christian, and Ali. Any of you out there, say hello. And while we're gathering up, folks, you'll be picking classes for next fall. If you have any questions on AP Chemistry, if you're in the diploma program, please let me know. It's a year's worth of college chemistry, so it's an intensive class, but a really good class. And I love teaching it. I've taught it for 20 years. If you're interested in something about it, write me an email, and I made a video that I can send to you as well. Hello, Tadashi. Hello, Tom. Okay, so when last we met, we were at school, or I was at school, and I did a couple experiments with you, and I want to share those now. Ah, there's Deacon. Good. Thank you, Deacon. So we want to talk about why these things happen. So we'll begin with experiment 1 and move our way through experiment 2. Okay? All right. For experiment 1, we have to talk about something we began with last time, but I think we ran out of time. Let's find out. Okay? So, periodic table. As you get closer to fluorine, we said that atoms pull the towards them more. As you get closer to fluorine, it's called electronegativity. What does that mean? So fluorine's the most electronegative. What does it mean? What's it attracted to? Can you remember that from last time? Well, 2 times ago. You'll see why I'm asking. Okay, good. So fluorine's very attracted to electrons, okay? The least attracted would be like francium way down here at the other end. Well, turns out that really matters, okay? And what matters about it is, um, that the electrons are pulled to one side. Ah, yeah, exactly, Vincent. Thanks for participating, everybody. The electrons are pulled to one side. Let's have a look. Um, let's take HF. I know that wasn't one of our chemicals, but if I have HF, turns out, here, I'm going to draw it like this. H, and then that's going to be my F, okay? H is pretty small. F's pretty big. And they're bonded together. But what happens is the electrons are pulled more towards this side. So this side is more negative, and the other side is lacking an electron because it's pulled and spends more times around the F, okay? Let me make a little key. So I'm saying that little thing is my hydrogen, and the big green thing is my fluorine, okay? It's good to make a key. You're going to make a lot of pictures in the next week or two as well. I'll try and make it the same size here. All right. Well, what that means, gang, is let's say I've got another one over here, and I draw it like this. Well, what that means is there's an attraction between them. Check this out. The positive side of this one's going to be attracted to the negative side of this one. And we call that dipole-dipole attraction. Okay, first off, let's start with this. We say, hey, HF has a dipole. Di is 2, you guys know that. Pole, it's referring to electrical poles. So it's not magnetic like north and south, but a dipole means it's got a negative side and a positive side, okay? So we call this a dipole-dipole force. And if it's a special one between hydrogen, and it is, and NO or F, it's called hydrogen bonding. So, boy, that's giving you a lot all at one moment. Let's first use the general term. Okay, so this is a dipole force. And it's not a bond, okay? If you haven't had chem much, bonds are between atoms. Bonds are between atoms. All right, like you had with me last year, there's what? Ionic bonds, covalent bonds, and there's metallic bonds, okay? Forces, or the other word I'll use is attractions, are between molecules. Oh, it's between this molecule and this one, okay? So forces, or sometimes I'll call them attractions, are between molecules. Okay. This is a special type of dipole-dipole force. It's called hydrogen bonding. So hydrogen bonding, I hate the word because it's not a bond. Okay, so Shilpa has a good point. She says, well, we talking about the experiment or just things in general? Yes, we're talking about things in general, Shilpa. We're getting to the experiment as fast as my little marker can go. All right? So, do we need all this for the experiment? Yes. Okay, so hydrogen bonding. Here's the German name, which I like much more, Wasserstoffbrücken. I like the idea of bridges. Probably all one word if I know German. Brücken. I assume that's got an umlaut. I can never really tell for sure. German speaker, is there an umlaut in Brücken, plural of Brücke? Let me know. If not, I'll erase it. Okay. What it is, so hydrogen bonding is a special, strong dipole-dipole force between, big surprise, between hydrogen, right? Hydrogen bonding between H and fluorine, F, oxygen, O, or N, nitrogen. And you know how you're going to remember that? A stupid way. Okay? The way to remember hydrogen bonding is hydrogen just wants to have fun. F-O-N. Is that cheesy or what? Okay? So, hydrogen bonding. Even though I say hydrogen bonding, and here's the part that I hate, it's not a bond, it's an attraction. I didn't name it hydrogen bonding. You can probably tell. It's an attraction or a force, okay? Attraction. Okay, now we're ready to talk about the experiment. Sorry that took so long. Questions from you before I start with the experiment. Questions about hydrogen bonding. To get it, you got to have an attraction between a hydrogen and fluorine, oxygen, or nitrogen. So look at this. Here's my fluorine, the big green thing. Here's my hydrogen. So clearly, if I have a box of HF molecules, I've got hydrogen bonding between the molecules, okay? Between the two atoms, there's a bond. That's not what I'm talking about. Between the molecules, there's an attraction. And it could be the other way, couldn't it? I could have another one over here, and this little hydrogen could be attracted to the next fluorine in the next molecule. So I could draw a bunch of these if I wanted to. Question from Sarah. Is there any other term for hydrogen bonding? No. Although, no, I take it back, Sarah. In some textbooks, I've seen it written as hydrogen bonds, which I don't like at all because it's not really a bond. But the only other term is German Wasserstoffbrücken. Okay? All right. And I'm hoping it has an umlaut because I see a bunch of yeses. Maybe that's what you're answering. All right. Any other questions from you? Yeah, Tadashi. For the positive and negative sides, could those be seen as charges? Yes, they are in fact charges. So Tadashi, what it means is the electrons spend more time by this atom. Okay, if I drew it in here, he would be like the nucleus, right? So the electrons spend more time over here, so this side has more of a negative charge. That's exactly right, Tadashi. And therefore, the little hydrogen is lacking its electron, so it has more of a positive charge because it's missing its electron. Yes. Okay. Anything else? Good questions? All right, let's hit our experiments. Okay, good. All right, so we want to talk about alcohols and stuff like that. And our first experiment, if you remember, experiment 1 was 50 milliliters, and actually it was like really exact, 50.0 water plus 50.0 milliliters of ethanol, right, an alcohol with 2 C's, equaled 98 milliliters about of the mix, which is weird. So why? Okay, I had some of you right at the end of the hour, I think Shilpa was one of them, who gave an idea that it probably has to do with something going on between the molecules. So now, now that you know about hydrogen bonding or hydrogen bonds or Wasserstoffbrücken, then now we can draw them. Okay, ready? Here we go. I'm going to let, I guess I'll let this be a hydrogen. That'll be an H. Let this be a C. Make it slightly bigger. And I'll let the green be an O. You can just write the symbols or whatever you want. Okay, so here's a water, right? So I got a water. I got water as H2O. Now careful, because I've had people screw that up and put 2 O's. There's 2 H's, right? So let's kind of do it. So here's an O, and here's a couple of H's attached to it. It should look like Mickey Mouse. They're not across from each other, just the way it is. So that's a water. Let's draw another water. I'll draw one over here. I'll just draw it orient a little differently. They're all floating around randomly. Now we're going to draw an ethanol. Okay. First off, let's draw one with a structural diagram. Okay. So ethanol is going to look like this. I got 2 C's, and then I got some H's, and then I got an OH. All right. Now there's a bend at the OH. I don't know if I told you that or not. That's important. And there's a bend in the water molecules. That's important. What's going to happen is you can guess, right? I got other H's here, by the way. I know I got other H's. I got H's here, 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 here. But those are less important. What's really important in the ethanol is these two, the oxygen and the hydrogen, because who likes electrons more, oxygen or hydrogen? Who likes electrons more, oxygen or hydrogen? Hint, who's closer to fluorine? I'm going to wait for your response because I need to know that you're thinking. You got it. Oxygen. Thank you, Lily, Tom, and everybody. Good. And Lee and others. So what that means is I've got more attraction here and I've got more electrons. So this side with the O is more negative, and this side over here with the H is more positive. So my dipole is not the whole molecule, but it's the end. Okay? See what I'm saying? 2 poles. I got a dipole at the end. Now, you also can guess with water that I got the same thing happening, right? The water has an O. That's more negative. And the H's are, that side is going to be more positive because the electrons have been stolen away and are more around the O. So this side of the molecule is more positive. And that, my friends, is super, super, super important. You need to know that water has a dipole, okay? And so does ethanol. So, hey, we can say, hey, both have dipoles. And da-da-da-da, they have what? They have H and O. So I don't just get dipole-dipole forces, I get so between them. Between H2O and ethanol. And now you'll see, Shilpa, why I had to do that. Thank you, exactly. Hydrogen bonding attractions. You got it. So hydrogen bonding. Now, a lot of 10th grade chemistry is drawing stuff. So that's why I'm going really carefully with you. Yeah, Lee had that too. Thank you, Lee. So, and others. So we got to go really carefully about this. Okay, so we're going to draw a connection now, an attraction between this guy and this. So really, I want to orient it so the H is sticking. Maybe I can make the H stick up here. Here we go. Let's try and draw an ethanol. Ready? I'm going to draw the OH first. Okay, so there's the, I want the, that's the O here. So I want the H of ethanol. Remember, I got other H's here, but I don't care about them. They're not attached to F, O, or N. These H's don't matter. Do they do hydrogen bonding? No. They're not attached to fun, F, O, or N. Okay, so, all right, shut up. My oxygen. And now let's draw some C's. So I got that guy is attached to CC. And I'll draw some more H's over here. This guy has two H's. This guy has three at the end. 1, 2, 3. And now the really important thing. Oh, I know this guy's more positive, and so there's going to be an attraction between here, won't there? I'm going to erase that for a sec and put the negative here. Yeah, so this is going to be a hydrogen bonding here. But you know what? There'll be more, so I'm going to draw some more in the picture. How about this? Let's put another water down here. Remember, this side is negative. So look at that guy. There might be then the H's on the next one might be interested in that. So the H's here of the next water, there's an O, so there's another water. Oh, so I have more hydrogen bonding. Do you see that I'm really careful about which side is facing which? Okay, Ali, you'll have to see the rest of the video because you missed quite a bit. Okay, so I'm really being careful here about how to do this. I guess you get the idea. So I could even put another one maybe in between here. Another one, another ethanol. And let's see how I want to do it. I can't really. I can put it in between here. So let's do it this way. How about I got I'm sorry, I'm thinking without telling you what I'm doing. I'm going to draw another ethanol. Okay, so let's draw one like this, and then I can add all those H's. But I don't really care much about them, but there they are. And now I got some more hydrogen bonding. Oh, look at that! I got this side is negative, and there's positive here, so there's going to be some here, and there's going to be some. I'm going to move this over. This will minus. Going to be some attraction between the positive here and the negative on the water molecule. So lots of hydrogen bonding. Whoa, shaboom, 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 shaboom. Okay, back to our beginning. I'll take your question in a second, Lily. 50 plus 50 equals 98. Well, you can guess why. What happened? Like Larissa said, it got denser. So they got denser because what did they do? All right. They moved closer together because they're attracted with hydrogen bonding. Aha. And when they moved close together, they also gave off something that I could feel in my hand. I'm going to write over here without destroying my picture. And then we'll take your questions, I promise. So we're going to say, oh ho. The water and ethanol molecules attracted and moved closer. Taking up less space. So it didn't add up to 100, it added up to 98. And the movement, when they moved closer, I'll just say the moving gave off what? I wish you could have felt it in your hand, but I couldn't have you feel it because you're out in the internet world. Okay? And this one I should do in red probably. Thank you, Magdalena, Shopa, and Sarah. So it gave off heat when they moved together. That's really typical. Okie dokie? Okay, let's take Lily's question and other questions you might have. That's complicated, but that's 10th grade. So see if you can ask me anything if it's not clear. All right, here we go. You're having trouble seeing the colors. Would you mind putting out the circles? Okay, here we go. I'm going to bring this closer. Okay, so Lily and others, the colors are less important than the sides of these things, okay? Like on water, it's important the O sides are negative and the H sides are positive. Check that out. Negative, positive. Here I didn't even mark it, so I got positive, negative, and they're going to be attracted to the opposite charges on the ethanols, okay? So on this ethanol, this side's positive, so it's going to attract to the negative part of water. And this negative part of the ethanol will attract to the positive part of the next water. So it's like the whole thing is all about opposites attract, okay? Check it out over here, same thing. Here's an ethanol, the H side is positive, it's attached to the negative side of the water. Here the O side is negative, it's attached to the positive side of the other water. I can draw lots and lots of waters and lots of ethanols if I have lots and lots of time. I hope that helps putting it closer, okay? But I can't hold it like that all day. Okay, here we go. Any other questions from you before we go to experiment 2? You're doing just fine. Anything else you should ask about? If it's not clear, ask me. Okay, for experiment 2, maybe I'll use, instead of I'll use symbols, I'll use structural formulas to make it a little quicker. but I want to use symbols once too with you, okay? Okay, so is the volume change constant? If I had 100 milliliters of each substance, wouldn't you end up with 4 milliliters decrease in volume? Yes, I think it is, Shilpa. So if I had 100 plus 100, instead of being 200, it would be like 196. I think that would be true. I think they would move together in the same amount of space difference. The more you had, it would be in the same proportion is the word that we're looking for. Good question. How many hydrogen bonds can a molecule have? Magdalena, as many will fit around it. Okay, here's another one. You see my water molecule? All right, I'm going to turn it and I'm going to face it. Okay, it's a three-dimensional idea. Okay, look at that. Here's the O. So I'm going to face my H's over here. Okay, so I'm going to face the ethanol with another water out here. So what I want you to know is I'm drawing this Magdalena in 2 dimensions, but often I can have 4 or 5 or even 6 waters around these different ends, sometimes less, as many will fit physically around it. Think of it. So there's my water, and I can have different things coming from different angles, 3-dimensionally, to be attracted to the water molecule, okay? So I can have several things. Okay, any other questions from you? Good questions? All right, let's go on to experiment 2. So that was experiment 1. The hydrogen bonding idea we'll see all year long, well, all semester long, okay? All right, experiment 2 was about solubility. Solubility means how well things dissolve. Let's take one of the easy ones we had. Yes, Magdalena. Let's take, we said water, well, let's put it this way. Salt, NaCl, dissolved in water. Okay, this time I'll draw it a different way, okay? Not to confuse you, but just to give you some choices. This time I'm going to draw my waters like this. Okay, here's the water. And I know this side's positive, the other side's negative. I know that. I'll mark it though, just to be nice. So there's positive, this side's negative. Water's the same everywhere. Okay, what about NaCl, folks? Which part makes a positive ion? Which part makes a negative ion? Which part is which? Like NaCl, which thing ends up being positive in water? Which ends up being negative? You should remember that from last year. Tell me about NaCl. It's an ionic bond. So what ions are there? What charge does each thing have? I know you had it because I taught it to you. Na has what charge? Cl has what charge? I need to know you know that, so I'm going to wait till I get a response here. There's some responses. Thank you. Good. Good. Thank you, Sarah. Exactly right. And Maryla has it as well. So here's what that means. If this guy's positive and this guy's negative, we're going to draw some down here and we're going to reflect that. Okay, now you should know this already, but anions, the negative ones, are bigger than cations. Why? Because they got more electrons. I'm going to write that. Anions are bigger. So I'm going to put this. I'm going to say, okay, I got a Cl minus, like that, and I'm going to have an Na plus, like this. That's going to be smaller, all right? You tell me where to draw them. Which one's going to be where? Which one will be on the H's side? Which one will be on the O side of water? So describe for me, where do I draw these in my picture? What would make the most sense? Opposites attract. There we go. Thank you. Good. And Noah says CO by the H. Good. So let's draw it. So I got a CO minus here. And I got a Na plus over there. And that's from Marla and Shilpa and others. Well done. Good. So I got Na plus over here. Opposites attract. Na plus. Here's what happens. It's not just two ions. A whole bunch are in there. And it's not just one water. A whole bunch are in there. So you know what? I can draw more of these suckers. You ready? Watch this. Here's another water. I'm going to have its little O face the Na plus. Check this out. Here's another one. Okay, here's another one. Here's another one. Does that really happen in water? Yes. Does it really look like that? Yes. Neuroscientists can figure out this is exactly what it looks like in water. Except that what? There's another one probably out here because it's three-dimensional. Another one behind the board because it's 3D. Same with another one here by Cl minus. I can fit another one here. Okay, maybe I can put one here. Let's put the H's. Let's put an O and let's put some H's here and here. Oh yeah, see, right? Because opposites will attract. The H's will attract the Cl minus. There's another one over here. Let's put some over here. Whoa, sorry, H's. And here's the opposite. Let's move this sucker over maybe a little bit. So H. And then the O's are going to face Na pluses. Whoops, I'm doing that in black, sorry. And then I'll have some more waters out there. Whoa, I'm losing track of this. Look at all these freaking markers in my hand. Well, the negative O's are going to be attracted to these guys. I can draw a bunch like that, right? Maybe one more for grins. Now, this is not dipole-dipole attraction because I don't have dipoles. What I do have are ions. So guess what? This is all connected. Water dissolves well because it's attracted. No, sorry. Salt dissolves well because it's attracted to the waters by ion dipole forces. So, ooh-hoo. Salt dissolves in water due to strong, that's why it falls apart and attracts the water, strong ion dipole attractions. And let's underline that because that's a new term. You might say, but Mr. Wise, how many of these attractions are there? About 4. So relax. You've already had 2 of them. You've had 3 of them already. You've had dipole-dipole, which we haven't done an example of. We've done hydrogen bonding, and now we've done ion dipole attractions. There's only so many, so don't worry. There's not an infinite number of different attractions. But If you were the salt, it's like you fall into the water and you go, oh, water. I love water. Bye, NA plus. I'm going over to the water. Sorry, bye. So they break up and want to go and attract to different. CO minus is like, ooh, look at all those H's. Oh, I love it. And the little the Na plus says, oh man, look at all these O minuses. Aren't they beautiful? So they go and attract to all these O's on the sides of the waters. It's what they do. So NaCl falls apart. It's more attracted to the water than it is to itself. Okay, let's see what questions you have. Wouldn't the hydrogens repel? No, they're bonded, Magdalena. The hydrogens are attracted to, they're bonded to the O's. Do you mean would they repel apart this way? Well, it turns out I can't have that. You'll find out, Magdalena, in 11th or 12th grade, but it's not straight. Water is bent. Has to do with where the electrons are allowed to physically bond around the atom for oxygen. So it really is bent. So no, they can't really repel away from each other. The H's really stay on the same side of each of the molecule. The H's are stuck there, and the O is kind of on its own on the other side. Okay, Lily, what are the names of the two other kinds? Well, I'm going to give you those, Lily, as we do them. Okay, because I don't want to like roll over you with a truck. I'd rather just hit you with a VW bug, one thing at a time. Okay, so I'll bug you with one thing at a time. Okay, we okay so far? Okay, so this is why water dissolved in salt dissolved in water. Okay, so the salt dissolves in because we got strong ion dipole attractions, and apparently they're stronger than the attraction between the ions in the salt crystal, right? They must be. Let's go on and do another picture. Another picture. Okay, I'm going to erase this. So a picture is worth 1,000 words. That's what they say. And it really is important. What I'm doing is I'm trying to train your minds. I want you to think like this because this is the way scientists think the particles are. If you can think like the particles, you're there. Okay? You're there. You're understanding the chemistry. Let's do another one. Okay? I got to think back on what we did. Okay, we had water dissolving in ethanol. We did that already. We had salt dissolving in water. Now let's look at, did we use hexane or pentane or heptane? What did we use for the alkane? Which one did we use, gang? Because I didn't write it down in my notes. What alkane did I use with you? Pentane, hexane, or heptane? What did I grab? Heptane. Thank you, Sarah. Okay, so heptane did not dissolve in water. Why not? Well, you guessed it, Chester. We're going to draw something to explain it. But I'm going to give you the overall rule first. Okay? The overall rule is like dissolves like. What does that mean? Like dissolves like. Okay, what it means is if I got something with a dipole, so dipoles dissolve in other dipoles. And something we haven't drawn yet, but we're going to draw now, is a non-dipole. Non-dipoles dissolve in non-dipoles. And then we'll answer Lily's question too about one of the other forces. Whoa, boy, that was a quick 45 minutes. Okay, we're not going to then finish that up till next time. And next week, we're going to get far enough so that I'm going to assign you to do some drawings next week. Next week's not a full week because we got like parent teacher conferences and we got a day of meetings on Thursday. So I don't know how often I'll be seeing you next week. Okay, that's it, huh? Wow. All right. So my people, I'll write down and we'll continue with pentane in water next time. No, heptane in water next time, and we'll draw that. In the meantime, I think I'll just wish you a good weekend. I sent you the alcohol sheet. Maybe run it off, print it, and then just fill in the things. You don't have to tell me you did it because it's not really much of an assignment. Just fill in the blanks, and we'll see you next week. Okay? All right. More fun next week with drawing. Stay healthy till then. Bye bye.